hybridization on this atom here. This is our shorthand notation for organic compounds. So at each junction point, we're going to have a carbon atom. We show the carbon-carbon bonds. So it means that we have a single bond between two carbons and a double bond between two carbons. That's only 3 bonds. That's not enough for hydrogen. So what we're not showing, that's not enough for carbon. What we're not showing are the hydrogens. That means that carbon really has a single bond between a carbon, double bond between the other carbon, and then a hydrogen attached onto it. That means we have 2 single bonds and a double bond, 3 areas electron density, so a trigonal planar geometry. Trigonal planar geometry hybridization is a sp2 hybridization. So we need 3 sigma bonds here for our 3 areas electron density. That means we need 3 atomic orbitals to be hybridized together. So we're using 1s and 2p orbitals to hybridize them together to create our trigonal planar geometries, our 3 hybrid orbitals to give us our trigonal planar geometry. Our bonds we identify as being sigma or pi. Sigma bonds are on bond axis. Our pi bonds are above and below bond axis. So a double bond between 2 carbons, the sigma bond is a pair of electrons directly between the 2 carbons. So this would be our sigma bond. Our pi bonds are formed from unhybridized p orbitals. The p orbitals stick above and below the bond axis. And what they do is they overlap above and below. So this is our pi bond, and it's 1 pair of electrons that is both above and below that bond axis. So every bond starts off with the sigma bond, and then additional bonds, double and triple bonds, will be pi. So a triple bond is going to be a sigma and 2 pi bonds. So overall in this molecule we have 3 sigma bonds and we have 2 pi bonds. So when we have a triple bond here, 1 pi bond is going to be above and below, and the other pi bond is in front and behind. So the pi bonds are going to be rotated 90 degrees from each other. So they're not on top of each other, they're rotated 90 degrees from each other. For molecular orbital theory, what we're doing is we're taking our atomic orbitals and blending them together. The number of atomic orbitals that goes in will equal the number of molecular orbitals coming out. We're doing homonuclear molecules. That means we're 2 atoms, 2 identical atoms together. This makes it easy because these energies come in at the same level. If we take 2 different atoms, the energies come in at different levels, and they don't always blend together in this fashion. And the further apart, the more likely they are to do crossover blends of a P blending with a S and stuff like that. So for our homonuclear, our S orbitals are going to, 1 S orbital from each atom blends together to create 2 molecular orbitals. And when we blend them together, we're always going to get an equal number of bonding orbitals and anti-bonding orbitals. So our S, when they blend together, form sigma bonds. Our P, when they blend together, are going to form sigma bonds and pi bonds. So again, the pi bonds are above and below the bond axis. Sigma bonds are directly on the bond axis. So our 3p from 2 different atoms, a total of 6 orbitals, will give us a total of 6 molecular orbitals, 1 sigma bonding, 1 sigma anti-bonding, 2 pi bonding, and then 2 pi anti-bonding. So once we have the structure, and this structure here with the sigma being lower than the pi works for oxygen and larger elements. For boron, carbon, nitrogen, these two will switch positions. So for F2, we have 7 valence electrons from each atom, so a total of 14 valence electrons. So we start to fill them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So after we fill in our electrons, now we're going to write our electron configuration, working from low energy up toward high. So we have a sigma 2s. I didn't write the 2 in there, so sigma 2s, and it has 2 electrons in it, so we use a superscript 2. Sigma star, the anti-bonding, coming from 2s, and again with 2 electrons in it. Then we have our sigma 2p with 2 electrons in it. Then our pi 2p, and now this has 4 electrons in it. Our antibonding pi star, and that also has 4 electrons in it. So that is our molecular orbital electron configuration for an F2 molecule. For O2, again, for oxygen, we're going to have our sigma p lower energy than our pi p oxygen in larger molecules. We have 6 valence electrons for each oxygen, a total of 12 electrons. So we put them in. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we put in our 12 electrons. This is going to tell us a couple things. First, I'll answer the bond order. So bond order is bond pairs minus antibonding pairs. Or if we're dealing with electrons, is half the bonding electrons minus the antibonding electrons. So bonding electrons will be 2, 4, 6, 8. Antibonding electrons will be 2, 3, 4. But we're dealing with electrons, so we're going to divide these by 2 to get pairs or bond order. So our bond order is going to equal 2. So we have a net of 4 bonding electrons, but bonds are compared to 2 electrons, so we divide by 2, and we end up with 2 bonds. And this is what we get when we do our Lewis-Dot structure. Lewis-Dot structure will give us a O, double bond O. So our molecular orbital generally agrees with the Lewis-Dot structures that we draw. Another thing that we can get out of this is that we have unpaired electrons here. Unpaired electrons means that this molecule is going to have a magnetic moment to it. That means it will be pulled into a magnetic field. So whenever we have unpaired electrons, it's going to be a paramagnetic molecule. If we only have paired electrons, as we do down here, this is diamagnetic. And diamagnetic molecules are pushed away from magnetic fields. Paramagnetic molecules are pulled into magnetic fields.